Alright, so we're going to try this again, because you know what totally sucks is when you record this one time and for some reason it doesn't save, and then all of a sudden you're like, crap, and do it all over again. So section 1-5, infinite limits. I'm going to apologize for my voice here right off the bat. It's almost 11:20. I just watched the Indians lose, and I'm tired, and I want to go to bed. But I'm doing this for you guys, because I know you love calculus. So two topics left, infinite limits and limits as we approach infinity. Hopefully they go well, and we'll be moving on to the wonderful world of derivatives here shortly. So let's start off the notes here today. I'm going to take a look at this function, 3 over x minus 2, and just talk about what's happening as x approaches 2. If you were to take this and graph it on your graphing calculator, you should have a graph that roughly resembles what I have here drawn on the board. And that is that we've got a vertical asymptote at 2, and that we've got two parts of our function. One is heading toward negative infinity, and one is heading toward positive infinity at some point. So if we talked about the limit of this function as we approach 2, hopefully you would tell me that the limit is a big Lindsay Lohan. It does not exist, okay? Even though it's not October 3rd, it's October 27th. The limit still does not exist. If we think back to what we've talked about over the last couple of days in terms of one-sided limits, we can start to kind of really describe what's happening with our function as we approach 2 from the left-hand side. So as you kind of follow the cursor here, as I approach 2 from the left, you see that our function is going down, 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 further and further down to the point where we could say that it's heading toward negative infinity. Likewise, we could talk about what's happening to our function as we approach 2 from the right-hand side. As we approach 2 from the right-hand side, we can see that that function is increasing very rapidly and heading toward positive infinity. So these one-sided limits that we've talked about over the last couple of days actually now give us a way to describe what is happening with a function as we approach a given value that might be an asymptote. We don't have to stick with the traditional, oh, it does not exist type of answer. We can actually be more descriptive and say, hey, you know what? As we approach 2 from the left-hand side, we're getting closer to negative infinity. As we approach 2 from the right-hand side, we're getting closer to positive infinity. So when we talk about an infinite limit, we can say that an infinite limit of a function, that limit increases and decreases without bound as x approaches whatever given value we're talking about. Of course, we give it that generic representation of c. So the big thing you want to do here is you want to look for where you've got vertical asymptotes. Alright, that's going to be one of the key things we talk about in this section as well. How to find vertical asymptotes, what's happening as we approach a vertical asymptote from the left, from the right, and those will provide us with those infinite limits that we just saw. Apparently I can make things change color without even doing anything. It's kind of weird. So as we take a look at a couple of examples here, again, a lot of what we're going to be looking at are rational functions. Something where the denominator has the variable in it, like 1 over x. Graph that in your graphing calculator. It's going to look similar to what we saw just a second ago up here, but not quite the same, because now that asymptote is at 0, which is why when we talk about the limit, we're going to look at the limit as x approaches 0 from the left, and the limit as x approaches 0 from the right. And as you look at your graph, you should see that as we approach from the left, we're heading to the negative infinity. As we approach from the right, we're getting closer to positive infinity. Very similar to that, if we were to take a look at the function 1 over x minus 1, where's that vertical asymptote going to be? It's going to be at 1, because if I put 1 in for x, my denominator is going to equal 0, and that's not good. Kind of like Wreck-It Ralph. That's bad, and that's good, and that, I don't remember. Sorry, it's late at night. What's happening as we approach 1 from the left? What's happening as we approach 1 from the right? Again, we're going to head toward either infinity or negative infinity. And so again, this just gives us another way to describe what's happening as we approach a given value from one side or the other without always having to sit there and say, well, it does not exist. It does not exist. I know that's the easy thing to say, but life's not always easy. We can find ways to describe the situation a little bit better so that people, aka me, have an idea of what you're actually talking about. Alright? So, vertical asymptotes. The best way, or one of the easiest ways to figure out your vertical asymptotes is to take your function, look at your denominator. If you have a variable in your denominator, take that entire denominator and set it equal to 0. Why, you ask? Because that's the value that you don't want. And so in order to figure out what's going to cause that to happen, the best thing to do is just to go ahead and make it happen. Set that equal to 0. Solve that equation. And when you do, you find out that x equals 1. And so in this case right here, we would have a vertical asymptote at 1. So we've got a couple other examples here for you. Try this second one on your own here briefly. If you want to pause, pause. Okay, we're back. So hopefully you took that denominator, you set it equal to 0, you solved, and you got not just 1, but also negative 1. And that's where your vertical asymptotes would be located. And it wouldn't be a great math class if we didn't talk about trigonometry along with the unit circle. So cotangent of x. Your best bet here is we don't know a whole lot about the cotangent of x. And some of you probably don't really care to know a whole lot about the cotangent of x. But in terms of figuring out the problem involving the cotangent of x, your best bet's probably to change it into something that you're more familiar with. We know that cotangent's really 1 over tangent. But again, tangent, what does that tell me? Not a whole lot. So at that point, remember that tangent is sine over cosine, which means that cotangent is the reciprocal of that, which is why we have cosine x over sine x here. You'll see that I have the sine of x highlighted. Why? Because, well, it's in my denominator, which means I want to try to figure out what's going to cause the sine to equal 0. That's right, that's where your unit circle comes back into play. Where does sine equal 0? East and west. Alright, at 0, at pi, at 2 pi, at 3 pi, 4 pi, 5 pi. But that would be such a pain in the butt to sit there and have to write out all those different values of pi. And so what we do is we can kind of write it as an expression, and that's where this highlighted area comes into play. It's 0 plus or minus k, and that's the letter k. K is going to represent some type of integer, positive or negative whole number, times pi. And so this expression pretty much represents every single place that you would have a vertical asymptote for the cotangent of x. And we'll talk more about that when I get back to class on Monday. Alright? So hopefully you've survived the notes so far. We've got a little bit more to go. Everything's kind of in the way. There we go. So with rational functions, if your rational function ends up with some number over 0, then that pretty much tells you that you've got a vertical asymptote. And that's kind of what's happening in all these examples that we're looking at here. Our denominator is becoming 0. We have something that's not a 0 in the numerator, and so that's why we're getting those vertical asymptotes. However, if we do end up with something where, excuse me, we get 0 over 0, that's our sign. Sign, 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 sign. Everybody. Thanks, Owen. Appreciate you throwing that in there, bud. You want to keep looking. Alright, for example, and I apologize, I had this all described out before and not written out, but, take 2. If we take a look at our denominator here, x squared minus 4, we can see that we should have a vertical asymptote at positive 2 and negative 2. But if I take that positive 2 and I substitute it into my numerator and I substitute it into my denominator, I get 0 over 0. Which means, you know what, there's something going on, there's something we can do. You've got a polynomial here, you've got a polynomial there, which means, hey, try to factor. And when we factor, you see that this becomes x plus 4 and x minus 2. We know that our denominator becomes x plus 2 and x minus 2. Well, you've got the same factor in the top and the bottom, so guess what? Those cancel out. What does that tell us? So glad you asked. That tells us that that value of positive 2 where we thought we had an asymptote at, really was just a hole. It was a removable discontinuity that we now have removed, and the only asymptote that we have left is where x equals negative 2, because here negative 2 would cause this to equal 0. And so that happens sometimes, where you can simplify functions, and where you thought you had an asymptote, you really didn't, or you really don't. You have an asymptote somewhere else. Alright, so there is no vertical asymptote at x equals 2, because you can factor the function and simplify it. Kind of like this next example here in green. Same type of thing is going to happen. Right? It looks like I've got a vertical asymptote at positive 4 and at positive 2. I'm going to take that polynomial, I'm going to factor it. Once I factor, I'm going to solve each factor and get 4 and get 2. Well, the good news is this. I can also factor my numerator, x plus 2, x minus 2. Common factor here and here. And so those factors will cancel out. That means I had a hole at 2. I still have a vertical asymptote at x equals 4. That might cause some confusion. I'm sorry if it does, but if you can factor and cancel, that was a hole. Whatever's left, if you can't cancel out with anything else, that's an asymptote. Alright? So, one last little slide left here. It's on properties of infinite limits. Very similar to some of the things we've talked about in the past couple of days. Like basically what it boils down to is this. I'm going to take the limit of two functions, f of x and g of x, both as x approach c. No, no. Maybe if I do it this way. Yeah, because I forgot to put that in here. Sorry. There we go. So both as x approach c. Well, the limit of f of x is going to be infinity. The limit of g of x is going to be represented by L. L just represents a number. Think about it as like it's 2 or it's 4. Maybe it's negative 1. It's just a variable, essentially, to represent some specific value. So, if we were to take the limit of the two functions added together, wow, that was loud in my ear. If we were to take the two functions added together, then that's nothing more than just the limits added together. So if I took infinity and I added 2, what do I have? Essentially, I have infinity. Adding 2 to infinity is not going to change the value at all. It's like saying, hey, Bill Gates, you've got $40 jibillion. Let me give you 2 more. How much do you have? That's right. Essentially, you still have $40 jibillion. Because adding 2 doesn't mean jack squat to Bill Gates. He can just give that like to somebody else. Maybe give it to you as like a scholarship. That'd be pretty sweet. Alright, so adding or subtracting a small, minute value, like L, which again, 2, 10, 100, compared to infinity, it's nothing. So that's why this value stays as infinity. When you multiply, okay, infinity times 3 is not 3 infinity, it's not infinity cubed, it's just infinity. Multiplying by a value doesn't change the fact that it's a ginormous number that's so indescribable that we give it a sideways 8 to represent it. Alright, and so this works out to be positive infinity as long as this value of L, this one right here, is positive. If it's negative, then the whole positive times a negative comes into play and we get negative infinity. Okay, one of the last properties we have here, this is a good one. Alright, if we take the limit of g of x divided by f of x, which means we're taking that number and we're dividing by infinity. So think about this. Take your calculator, type in like 3 divided by 999 billion, and hit equals or hit enter. When you do that, you get like some number in scientific notation is like 10 to the negative 12th power or something. And that's because that number is so small that it might as well just be what I have written here. Yeah, that's 0. Okay, so taking a number, dividing by infinity is going to cause it to become really, really, really small. And so might as well just call it 0 because it'd be a lot easier. All right, so a couple examples here, kind of illustrating what I just was talking about with the properties. If I take the limit of 1, well, that's 1. The limit of 1 over x squared is x approaches 0 from the right is infinity. So if I was thinking to myself, what if I added those functions together? I wonder what my limit would be as x approaches 0 from the right-hand side. Well, that would be 1. That would be 1 plus infinity. Well, guess what? 1 plus infinity? Hi, it's called infinity. 1 plus infinity. That sucked. Equals infinity. There we go. All right. Same type of thing happens here. Let's get rid of that. Gone. If I add 3 to the cotangent of x, or I take 3 times the cotangent of x, excuse me, well, 3 times infinity is just going to be infinity. If I take 3 divided by infinity, like I said before, that's going to give us 0. We're taking something small and dividing it by something really big, and so that gives us, essentially nothing. What are we at here? 16 minutes. All right, we're almost done. Excellent. So here's what I would do. Go to page 88. Try problems 1 through 4. Go to 9 through 49, do every third problem. So it's like 9, 12, 15, 18, etc. Along with problem 62. Start this now. If you don't finish it in class, that's fine. Do it on Friday in class. Don't worry about taking it home. All right, we got shortened periods. I'll be back on Monday. We'll talk it all out. So hope you have a great weekend. Good luck to everybody this weekend, football game-wise, student section-wise, everything else. All right, and I'll see you guys on Monday.